Hello, my name is Prof. Skip, and I'd like to use this opportunity to show you an example of how you can use mesh analysis, in particular a super mesh analysis, to analyze a particular circuit problem. If you take a look at this problem right here, and we want to take a look at finding the value of Vx with respect to a ground reference, which we'll put right here. What you could do is you could label a loop current as I1 right here, and then you could label a second loop current like that as I2. And by inspection, I think you can clearly see that I1 is just equal to a minus 10 milliamps. And then you can continue on with writing your KVL, your Kirchhoff's voltage law equation, around that outer loop. That only puts one of those loop currents through that current source. That way, by inspection, you can label I1 as simply 10 milliamps. But there's another technique that you could use to solve a problem like this, and it's called super mesh. And let me show you how that works. I'll show you how to set up those equations. We'll get rid of that. And I'm going to define a loop current here as I1, and I'm going to define a loop current here as I2. Notice we have two currents flowing through the 10 milliamp current source. Now, I like to label my loop currents in a clockwise direction. That's the way that I present the material. It doesn't really make any difference, but to be consistent, I'm going to go ahead and label everything in a clockwise direction here. And if you take a look, you could write your loop equation, but when you go around loop 1, notice you have that current source to deal with. And if you go around loop 2, you also have the current source to deal with. When you see that loop currents share the same current source. I'll say that again. When you see that loop currents share a common current source, what you can do is you can label a super mesh around the entire loop. And when you do an analysis with the super mesh, the first thing you would do is recognize the fact that you have two currents flowing through the 10 milliamp, and I2 flows in the same direction as the 10 milliamp. So the first equation I'd write is if you take I2 and you subtract out I1, that's going to give you your 10 milliamps. There's your first equation at the super mesh. And then the second equation, we start at the bottom left-hand corner and you go around the entire loop, keeping in mind that you still have those loop currents I1 and I2. So if I start at the bottom left-hand corner and I go around the entire loop, you have a plus 100. I'm just using Kirchhoff's voltage law here. You get a plus 100 because you're going from a negative to a more positive. I'm starting here in the bottom left corner and going around. I have a minus 10K times I1. And I have a minus 10K times I2. And I have a minus 50, and that equals 0. And notice I have two equations now with two unknowns. And you can solve those simultaneously. And that's how you handle a super mesh. You first of all write the super mesh equation, I call it, with the currents that share the same common current source. And again, since I2 flows in the same direction as the 10 milliamp source, it's the lead current. So I2 minus I1 is equal to the 10 milliamps. And then around the super mesh, I just write a Kirchhoff's voltage law equation in terms of both I1 and I2, depending on which one of those currents flow through the passive element. Let me give you another example here. How about this example right here? And again, in this example right here, if you don't want to use a super mesh, you could define a current there called I1. And by inspection, you see I1 is 2 amps. As long as we don't assign any other loops that pass through the 2 milliamp source, you could do that. I could go ahead and I could define this loop right here as I2. As long as I don't pass any more currents through that 4 amps, I can say that I2 is equal to a minus 4 amps because it goes in the opposite direction. And then I could form another loop because I have to pick up the 6 ohm and the 12 ohm and the 3 amps. So what if I start down here and I go up around here and I come around here? Notice I included all the elements with all those 3 loops, but only one current flows through the current source. That'll work, and you can write your 3 equations with 3 unknowns. But that's not a super mesh analysis. Let me show you the super mesh analysis, at least setting up the equations. What I would do using a super mesh is I'd take a look and I'd notice that I could call this I1, I could call this I2, I could call this I3, and I could call this I4. And by inspection, I think you could take a look at this and you could clearly see at the super mesh, at that super mesh, I get an equation. And that equation is going to say I2. And by the super mesh, I mean the 2 loop currents that share the same current source, which is I2 and I3. So I2 minus I3 has to equal 4. So there's one of my equations. The second equation, I can see by inspection, I1 is simply equal to 2 amps. In the third equation, I can see by inspection, I can see that I4 is equal to a minus 3 amps. Now the only other equation I need is around the super mesh. So let me do it in red so you can see where I'm going to start down here and make sure that you pick up the other elements, but do not go through any other current source. You have to be careful. That's my closed loop. So the fourth equation is simply going to be starting at the bottom, left-hand corner, and going around that. You have to be real careful with the currents now. I say a minus 6, and the lead current there is I3 minus I1. And then I see the 12 up there. I say minus 12. And the only current that goes through that is I2. And then I see a minus 6. Then I stop and think, what currents do I have gone through that? Well, the lead current is I3 minus I4 equals 0. Now, I'm not going through the algebra here, but there's your 4 equations with 4 unknowns. I tell everybody, just get them in a standard form. Once you get these network equations or these system equations, they're real easy to get. Don't try to use algebra to solve them. I mean, I'd put the first one in a standard form, and I'd basically take a look and say, well, that's a 0 I1. I'm just taking this. I'm getting this in a standard form here. Plus 1 I2 minus 1 I3 plus a 0 I4, because it's not represented, equal 4. So I get a 0 I1 plus 1 I2 minus 1 I3 plus 0 I4 equal 4. The second one, in the standard form, I get a 1 I1 plus 0 I2 plus 0, plus or minus 0 I3, because the coefficient's 0, plus 0, so that could be plus or minus, plus 0 I4, and that's going to equal 2. take a look at that. That's your standard form for that equation right there. This one down here is a 0I1, the third one, plus 0I2, plus 0I3, plus 1I4, equal minus 3. And then simply get this last one in a standard form. And then using matrix or determinant algebra, or just on your smart device or on your calculator, plug in the coefficients, plug in the constants, and you can solve for the currents. In this particular problem, we wanted to find I. So if you take a look at the original circuit there, the way we defined these currents, I think you can see that I goes from top to bottom through that 6 ohm resistor up here, right here, I, right there, I. So I3 is the lead current. So I is simply going to be equal to I3 minus I4. Goes in the same direction as I3. So I3 minus I4. And once you solve that for I3 and I4, that gives you your answer. So I hope this short video showed you how to work with mesh. Some textbooks call it loop analysis or mesh/loop analysis, and how to handle super meshes. There's 2 ways to handle super meshes. Just define currents so that loop currents, such that only one loop current goes through each particular current source. But you don't have to worry about that technique if you use a super mesh. And the super mesh analysis works as well. I hope that this video helps.